Last class we discussed the operation of a buck converter and the boost converter. We derived the transfer function for buck as well as boost converters. For a buck converter, the transfer function is, or V naught is d into VDC, provided current is continuous. In other words, inductor current IL is continuous, output voltage is given by d into VDC. It is independent of the load current, independent of the load or inductor current. We found that if the load resistance increases above a critical value, current may become discontinuous, and if the current is discontinuous, the voltage is no longer equal to d into VDC. It is equal to d VDC divided by beta, where beta is the instant current becomes 0. It's greater than d, but then less than 1. Therefore, the output voltage is higher than d into VDC. Okay. The second observation was the ripple in the output voltage as well as the ripple in the inductor current. Current increases when the switch is closed and current decreases when the switch is opened. The both ripple in the inductor current as well as the ripple in the output voltage is a function of d. It is maximum when d is equal to 0.5 for a buck converter. We have derived this in last class. About the boost converter, ideal boost voltage tends to infinity when d is equal to 1. For a non-ideal boost, output voltage tends to 0 as d tends to 1. Why? In ideal boost, while deriving the transfer function, we had assumed that V naught is constant and ripple free. Okay. This may be true, or this will be true for low values of d. As you increase the value of d towards 1, most of the time capacitor is supplying power to the load. So therefore, capacitor voltage will decrease, and at the input side, inductor is almost permanently connected to a DC, so it will saturate. Current will be very high, VDC by R. So either the source or inductor or a switch will fail, and output voltage will become 0. Okay. So in this equation, in this circuit, this is when the switch is closed, capacitor is supplying power. If most of the time switch is closed, capacitor continues to supply power to the load, so it will discharge. I can't assume that this voltage will remain constant. Eventually it will become 0 when S is equal to 1. Of course, you cannot achieve that condition because something else will happen here. Okay. So output voltage is approximately equal to VDC if I consider the value of the resistance of the inductor. It increases till d is equal to d max, and it is given by 1 minus square root of R by R. This R is the internal resistance of the inductor and capital R is the load resistance, and this maximum voltage is given by this equation. So it is a strong function of the internal resistance of the inductor. So generally the thumb rule is a V0 divided by VDC could be of the order of 7 to 10. A good inductor. I told you how to design and fabricate a good inductor, using a leads wire or using a large number of thin conductors twisting together and using a ferrite core. In the process Q, the quality factor of the inductor improves. Okay. So if I use a good quality inductor, maximum value of V0 to VDC could be of the order of 7 to 10. Okay, 7 to 10. Okay. Now, the filtering requirement for the buck converter as well as the boost converter. What is the source current waveform in a buck converter? If the current is continuous, when I close the switch, whatever the current that was flowing through the diode starts flowing through the switch or from flowing through the source. So instantaneously source has to supply the current that was flowing through the inductor, and when I open the switch, the current becomes 0. Okay. So instantaneously there is a rise and instantaneously there is a fall. Okay. So current changes abruptly in a buck converter, the source current. Okay. So definitely you require the filter at the input side. What happens in the boost converter? The boost converter, the source is always present even during powering as well as or even when the switch is closed and when the switch is open. When the switch is closed also source is there in the circuit, and even when I open the switch, source is there in the circuit. Here current increases and in this case current decreases. So the source current waveform, if I plot, source current waveform is the same as the inductor current, it looks something like this. It's a smooth change. So if I select a inductor such that this current ripple is minimum or is very small, I can say that the source side is approximately a current source. Though I have a voltage source and an inductor, I can represent the input side, source and the inductor, as a current source. Current source in the sense current is approximately constant. In an ideal current source, current is always constant, whereas a non-ideal source, I can assume that the input stage for a boost converter is approximately a current source. I have an inductor as well as a DC source. Inductor is selected in such a way that ripple is controlled, so current varies within a small band. It increases when I close the switch, and when I open the switch, current decreases. So current is controlled within a small band. So I can represent the input stage of a boost converter by a current source. Okay. So I may not, or input filter may not be required, whereas a input filter is required for a buck converter. Current changes in a step, drastically changes. It starts with a finite value and comes to 0 abruptly. There is an abrupt change in the source current. So in order to smoothen the current, you need to have the input filters. Okay. Now let us plot the various waveforms for a boost converter and the current is continuous. We will assume that inductor current is continuous. Please, when I say current is continuous in buck as well as boost, it is the inductor current and not the load current. Load current is supposed to remain constant, because we are assuming V0 to remain constant, and this is true for invariably for low values of D. So here is the circuit. Switch is on for D into T duration, and from dt to t, D is on. So current increases from I min to I max, and from I max to I min it decreases from dt to t. Okay. So when I close the switch, the source current or the inductor current is same as the switch current, IS. IS I am representing as the switch current. I might have said IS is the source current in the buck converter, maybe this doesn't matter, but here I am saying Is is the switch current. Okay, so it, when I close the switch, this jumps to the current that is flowing through the inductor or through diode D, increases linearly. When I close the switch, it becomes 0. Okay, immediately the current that was flowing through S just prior to opening it starts flowing through the diode. So this is the diode current. Okay. So what is the voltage across the switch when the diode is not, when the diode is conducting? When the diode is conducting, V0 or voltage across the C appears across S. There is a short here, so V0 appears across S. Okay. So this is a voltage waveform, voltage across the switch. Vs is voltage across the switch, V0. And what is the voltage across the diode when the switch is conducting? It is V0 itself, because when switch is conducting, there is a short here. So this point gets connected here. V0 appears across D, or minus V0. Okay. Now let us calculate the ripple in the output voltage and ripple in the inductor current. For temporarily, we will neglect the resistance of the inductor and we will assume that output voltage remains constant. Delta V0 is neglected. So when the switch is on, what is the input side equation? L di by dt is equal to VDC. So the equation for current IL is equation for IL is I min plus VDC by L into T. Okay, this is the equation of the line, or slope of the line is VDC by L. VDC by L is equal to DIL by dt. So this is the equation for the inductor current when the switch is closed. I reaches Imax, or I is equal to Imax when T is equal to dt. I'll just substitute for T, so I'll get an equation for Imax. Okay. Now when I open the switch, what is the equation for the inductor current? L di by dt is equal to VDC minus V0. VDC minus V0. I'll substitute for V0. V0 is given by VDC divided by 1 minus D is equal to this. Should be negative, only then current will fall. In other words, V0 should be higher than VDC. That is the essential condition. So VDC minus V0 is given by dVDC divided by 1 minus D. Okay. Therefore, IL is given by this equation, and IL is equal to I min when T is equal to T. Okay, I'll just substitute for T. Okay. So this is, what is delta IL? Delta IL is I max minus I min, which is nothing but this term, this term. Okay. So you'll prove that, you'll find that, of course, 1 minus D get cancels with 1 minus D, so I'll get VDC divided by L into D into T. So therefore, ripple in IL is proportional to D in a boost converter. It's true, it is very obvious. In the sense, if I close the switch for a longer duration, IL increases linearly. So in a boost converter, ripple is proportional to T, it goes on increasing, whereas in buck converter we found that both dV0 and DIL, the ripple in output voltage as well as the inductor current is maximum at D is equal to 0.5. Okay. Now how do I determine the ripple in the output voltage? By the way, when the capacitor is charging and when the capacitor is discharging. When the switch is closed, capacitor supplies the load. Okay. So entire on period of the switch, capacitor is discharging. Okay, which is different. In a buck converter, capacitor is charging even when I open the switch. It starts charging somewhere in between 0 and dt. When the inductor current is higher than the load current, capacitor starts charging. Okay, so capacitor is charging in between 0 and dt, and it is continues to charge beyond dt in a buck converter. Whereas in a boost converter, you will see here in the equivalent circuit that capacitor is continuously discharging when the switch is closed. So we have assumed that V0 remains constant. Of course, it may change, but then V0 by R is going to be very small. Change in V0 is very small, so V0 by R is still smaller. So if I assume that I0 remains constant, dV0 decreases linearly. Okay, capacitor is discharging at constant current rate, so it is capacitor voltage decreases linearly. So okay, I will come to it. When does it charge? When does it charge? When I am saying that capacitor is discharging for the entire dt period, I will assume that capacitor continues to charge in the entire off period of the switch. I will assume. It may not be true. It may not be true. I will tell you under what condition it will not be true. Okay. So, but then if someone says that capacitor is continuously discharging when the switch is closed, and still it is discharging when the switch is opened, there is going to be a ripple, a high ripple in the output voltage. Let me repeat. If the capacitor is discharging even when the switch is opened, okay, it is continuously discharging when the switch is closed. Capacitor is continuously discharging when the switch is closed. Now it is discharging even when the switch is opened. It means that there is a significant ripple in V0. Having said that input is approximately a current source, I can safely assume that when the switch is opened, capacitor is charging. Okay. So if I neglect IL while deriving V0, this is going to be the equation. KCL at this point is the capacitor current should be equal to I0. Minus sign indicates that capacitor is discharging. So what is the equation for V0? What is this? Why am I saying V0 max here? It's because I assume that capacitor is charging when the switch is open. For the entire duration, capacitor is charging. Okay, so it is discharging and it's charging here. At this point, switch is closed again, and inductor current starts increasing. So that's why I am calling V is equal to V max, because if the current is continuous, capacitor is charging the entire entire off period of the switch. So just prior to closing the switch, capacitor voltage has attained the peak value. Okay. Now once I open the switch, capacitor starts discharging, which is not the case with the buck converter. They are different. Okay. Go back, draw the current waveform through the capacitor and through the capacitor for both buck as well as boost, and find out, okay, the difference. So this is the equation for the output voltage when the switch is closed. At t is equal to dt, just prior to opening the switch, capacitor voltage has attained the minimum, okay, because the moment I open the switch, okay, capacitor starts charging. In the sense, now current that is flowing through the capacitor is difference of IL and I naught. Okay. When I open the switch, the inductor current divides, some part flows through the capacitor and some part flows through the load current. Okay. Now you may say that I naught could be higher than IL. If that is the case, capacitor continues to discharge. Capacitor continues to discharge. So this is just not possible. Okay, it was discharging when the switch was closed. It should charge when the switch is open, because we assume that average voltage across the average output voltage remains constant. It discharges for some time, discharges for some other time. So average voltage remains constant. Okay. So IL has to be higher than I naught when I open the switch. So it is minimum when t is equal to dt. Okay. At this point voltage is minimum, at this point voltage is maximum. It is also equal to at t equal to this. So this is the equation for the capacitor voltage. This is the KCL at, or when the switch is opened, this is the KCL. Inductor current IL should be equal to C dV naught by dt plus V naught by R. I will simplify this and I will write, this is the final equation. This may not be very obvious. I will request you to go back and derive this expression. Now let me tell you one thing, the aim of the course is not to derive an equation or prove something. No. If you understand the working of the circuit, you can always write an equation. After all, we have used only KVL and KCL. There are only two passive elements, L and C, and an input DC source. You can always solve it and derive an equation. Okay. The basic aim of the course is that you should understand the working of the converter. Deriving the equations is secondary. I am not saying that is not important, it is important. If I understood, I can always write an equation and I can derive it, not a problem. Okay. After all, there is L, C and a maybe R and an input DC source. Life is simple. Input is DC. It is not even a sinusoid. So after doing some mathematical jugglery, I can write that delta V naught is approximately as this equation. Okay, is given by this equation. Okay. Now let us see about the discontinuous current. Okay. When will it be discontinuous? What is the average value of the source current? Average value of the source current is same as the inductor current. Okay. It is given by VDC divided by R into 1 minus d square. This we have derived in the last class. Average value of the source current is equal to the inductor current VDC divided by 1 minus d square. This we have derived in the last class. Okay. Now, if this value of current is higher than delta I by 2, okay, this is the ripple, inductor current is always positive, therefore it isn't continuous. Okay. So if this current is higher than this limit, okay, I naught is higher than this limit, therefore I is always positive. Okay. So this can happen only when I'll substitute here this condition. I'll repeat, when this source current, average value of the source current is higher than half this part, half of delta I, okay, then I is continuous. Now I substitute and I'll get the critical value of the load resistance R. So if this critical resistance is higher than the load resistance is higher than the critical resistance, inductor current is going to be discontinuous. Okay. I'll repeat, if the load resistance is higher than the critical resistance, inductor current is going to be discontinuous. It's true even the buck converter, but then condition to determine the critical value of R is different. We use the two different situations. Okay. Now how does the waveforms look like? They're simple. I'll just draw for the boost converter, and the remaining converters I will not draw. You may have to draw yourselves. Okay. So current becomes 0 at beta much before I close the switch for the second time. So when I close the switch for the second time, current starts from 0. Okay, current starts from 0 and comes down to 0. This is the inductor current. So source current, or sorry, the device current, the switch current is also starts from 0. Okay, it increases linearly, and when I open S, it becomes 0. Diode takes over. See now the difference here. Capacitor current. I have drawn the capacitor current here. Okay, is constant current. It is discharging at a constant rate. The moment I open the switch, it starts charging. Okay, it starts charging. When the inductor current becomes equal to the load current, capacitor current becomes 0. Okay, at this instant inductor current is equal to the load current, so capacitor current becomes 0. Beyond this point, inductor current decreases, capacitor starts discharging. Capacitor starts discharging, and when the current has become 0, capacitor, entire load current is being supplied by the capacitor. See. Okay, it continues to supply the same current till you close the switch for the next time. I am assuming that V0 remains constant. Okay. So if you see a continuous conduction period, see here, it is capacitor is charging for the entire off period of the switch, Okay. So at this point, just prior to closing the switch, inductor current is higher than the load current. That's why capacitor current is finite. And positive. It's positive. See, I'll repeat again. Just prior to opening the switch, inductor current is higher than the load current. That's why the capacitor current is positive. Okay, at this point. I close the switch, immediately the diode turns off, the entire load current is being supplied by the capacitor. Okay, Whereas in this case you will find that, okay, is a discontinuous conduction. At somewhere at this point, inductor current becomes equal to the load current. Beyond this point, inductor current is less than the load current. Capacitor has to supply the remaining current. So it discharges and continues to discharge till I open the switch in the next cycle. Okay. So capacitor is charging only for a shorter duration here, okay, and for the entire remaining period capacitor is discharging. Okay. Is a constant current here, here it is assumed to be linear. Okay, assumed to be linear. So that is the difference. Okay. So I am just using a Kirchhoff's current law to plot the current waveform, that is all. Okay. Now how does the voltage across the switch and the D and the diode look like? When the current is flowing through the diode, or when the diode is on, voltage across S is V0 itself. What happens when when the current becomes 0? Diode is reverse biased, okay. Sorry, diode turns off, no current is flowing through the diode now. No current is flowing through the diode. No current in this circuit also. So voltage at this point is VDC. Voltage at this point also VDC. No voltage drop across the inductor because no current is flowing. So VDC appears across S now. Okay. No current flowing here, is an open circuit. No current flowing here also. So potential at this point is equal to potential at this point. Okay. So that is nothing but the voltage across S. So VDC, it drops to VDC. Maybe for the better for the switch. Now voltage across it comes, voltage across it reduces. Okay. What happens to the diode? Cathode potential is V0 with respect to the ground. Okay. Cathode potential is V0 with respect to ground. What about the anode potential? Anode potential is VDC with respect to ground, isn't it? Just now I said that no current here, this point is same as this. So VDC appears across S. Now VDC is the potential of the anode of the diode with respect to the ground or the negative DC bus. Okay. So anode potential is VDC with respect to the ground, cathode potential is V0 with respect to ground. So what is the voltage across the diode? It is nothing but VDC minus V0. VDC minus V0. And V0 is higher than VDC, is a negative voltage. Okay. When the diode is, when the switch is on, it is V0. When the diode is on, voltage across it is 0. And the moment current becomes 0, it is VDC minus V0. Okay. Till I close the switch for the next time, and the cycle repeats. Okay. So drawing the waveforms is fairly simple. Okay. After all, KCL and KVL, only two theorems, basic theorems I am using. Now let us see what happens to the output voltage if the current becomes discontinuous. For a given value of D, what happens? In a buck converter we found that output voltage is higher than D into VDC if the current becomes discontinuous. So it is dVDC divided by beta, beta is less than 1. Okay. What happens in the boost converter? Okay. So we will see the same equations. IL is equal to VDC by L into T for 0 to dt. Current increases linearly here. Now I will open the switch at dt and current becomes 0 at beta into T. Okay. So during this period, voltage across the inductor is VDC minus V0. Okay. When the current becomes 0, voltage across the inductor is, there is no current flowing now. There is no current flowing to the inductor at all. So when the current is flowing, voltage across the inductor when the switch is open is VDC minus V naught. Okay. So the maximum value of current, or current has attained its peak when t is equal to dt. This is I max. Okay. It started from 0, initial value is 0. It started from 0 because current is discontinuous. When I close the switch, it starts from 0, it attains the peak at dt and starts decreasing, and this is what it is. This is the equation for the line when the switch is open. Okay, VDC minus V naught by L, and this is what it is. IL is equal to 0 when t is equal to beta into t. So I will substitute here. So it will become 0 only when this term is equal to this term minus. So you will get as V0 is equal to beta divided by beta minus d into VDC. Okay. So if beta is 1, that implies that current is just continuous. Current is just continuous. We still have the same expression, which is for an ideal boost. V0 is equal to VDC divided by 1 minus d. Current is at the boundary, in the sense current becomes touches just 0 at just prior to closing S. Okay. So beta is equal to 1, at the time you have same equation. Now beta is less than 1 and it is greater than d. You can find that beta divided by beta minus d is greater than 1 divided by 1 minus d. Okay. You need to be practical. You just cannot give arbitrary values. Okay. For all practical values, beta divided by beta minus d is greater than 1 divided by 1 minus d. Okay. So you will find that similar to a buck converter, output voltage is higher in a boost converter if the current is discontinuous. So V naught is higher than 1 divided by 1 minus d. Okay. That is true even for the boost converter. And when it is, suppose for given values of d, or for what values of d current is going to be discontinuous. If the value of d is very small, in the sense I am storing the energy for a very small duration, okay, and most of the time I am discharging whatever the energy stored is being dumped to the capacitor and the load. So I am storing it for a very short duration and dumping it or keeping the switch open for a longer duration. At that time, there are very good chances of you going in for, or inductor going in for, the discontinuous conduction current. Current is going to be discontinuous, or if you increase the value of R beyond a critical value, you will get a discontinuous. Now let us see where will I use this buck converter and boost converter in drives, okay, apart from power supplies. I have not told you the application of boost converter. I will tell you sometime later, where there is a very important application and a very elegant application also. And whatever that I told you in switch mode rectification, there also we called it as a boost converter. Remember, a closed loop control for a boost converter is a must. Closed loop control for a boost converter is a must. In the sense, you need to know the output conditions. It should not happen that accidentally the load that is connected across V naught is open circuited, and here you go on closing and opening the switch. As you go on opening and closing the switch, you go on dumping the energy to the capacitor, and there is nothing to dissipate. Capacitor voltage will go on building up. Okay. So closed loop control is a must, or in other words, we need to monitor the output voltage always. That is true in almost all the boost converters. Okay. Now coming to the application, see what I am doing is, this is a circuit, a DC source. I am taking two switches, S1 and D1. In fact, I do not need to connect a separate diode across a switch. Any controllable switch you take, either a BJT or a IGBT or a MOS, there is a built-in diode. Okay, this is a freewheeling diode or a diode that is connected across S, which is built in. I will take two switches, S1, S2, an inductor and a DC motor, the armature here. This is used to make the current continuous or to reduce the ripple here, or could be a filter inductor. Okay, could be a filter inductor. Now I will keep S2 open and S1 is controlled. In the sense, S2 is permanently open. That does not mean that D2 is permanently open. D2 is an uncontrolled device. Okay, you cannot control it. So I can control only on and off of S1 and S2, not D1 and D2. So I will control S1, I will use some duty cycle, close for S1, close S1 for some duty cycle, and I will open S1. Okay. What happens? See the equivalent circuit. S1, inductor, armature and D2. Okay. Though I kept S2, D2 will come in the circuit. What is this? This is nothing but a buck converter, or a step down chopper, Okay. EB is the back EMF, RA is the armature resistance, L is the total inductance of the armature circuit. Okay, is including the external inductor as well as the armature inductance. Okay. Buck converter, a buck chopper, V0 is equal to D into VDC, provided IA is continuous. Okay, I repeat, V0, it is this voltage, is equal to D into VDC if IA is continuous. Okay. So when I close S, IS starts increasing. When I open S, inductor current freewheels through D2. Okay, freewheels through D2. Okay. So by controlling the duty cycle of the switch S1, I can control output voltage and therefore the speed. Voltage applied to the armature will determine the speed of rotation. Omega is directly proportional to voltage applied to the armature. Okay. Okay. So if I have to control the current, I can control it in this fashion, or at steady state current increases, decreases for a continuous mode of conduction. For omega 0 to omega rated, D will vary from 0 to 1. This is about the buck converter. Having applied a rated voltage or having applied some voltage, motor has attained some steady state. Now you want to do a regenerative braking, or you want to stop the motor. Most efficient way is to do a regenerative braking, feed back the energy to the source. Okay. How do I feed it back? Okay. Now I will keep open S1 permanently, and I control S2. Okay. In this circuit, I will keep open S1 permanently and control S2. In the previous case, I had kept S2 open, S1 I had controlled. This is the circuit. VDC is the source, VDC is the source, and DC motor armature is the load. Okay, I'll repeat, this is the source, this is the load. Okay, V0 is D into VDC. If D is equal to 1, V0 is equal to VDC. Okay, but then that VDC is equal to IARA plus EB. Okay, this V0 is equal to IARA plus EB. So even if its D is equal to 1, even if D is equal to 1, EB is less than VDC. Okay, when D is equal to 1, V0 is equal to VDC, but V0 is equal to IARA plus EB. Okay, so therefore EB is always, back EMF is always less than this VDC source voltage. Okay, remember. Now in this circuit, I said I will keep S1 open and control S2. Okay, this is the polarity. Okay, with current was entering A when S1 was controlled. Now for regenerative braking, for motor to act like a generator, current should leave A. Okay, current should leave A. Now this becomes the source and VDC is the load. In the sense, VDC is receiving power. Source, the battery is receiving power from the load. Okay, now what I will do is this, I will call it as source and this will call it as load during regenerative braking. Okay, okay. Now just prior to closing S2 or just prior to regenerative braking, we are in the motoring mode, and we found that EB is less than VDC. Okay, in the motoring mode, when S1 was controlled, EB is less than VDC. Okay. Now see this figure, this is nothing but a boost chopper, a boost converter, wherein EB is the source, VDC is the load, okay, and condition should be VDC should be higher than EB. Output voltage V0 is always higher than the source voltage VTG for the boost converter to work satisfactorily. Same thing is true here. Just in the motoring mode, EB was less than VDC. Now we are going for regenerative braking. Okay, EB is smaller compared to less than VDC. Now I'll control S2. Okay, when I close S2, current starts flowing in this fashion. Now current is leaving A, store the energy in inductor, open S2, and it flows back to the source, flows back to the battery. Okay, flows back to the battery. Okay. So this is nothing but a boost chopper feeding back the energy to the source. Okay, actually now we are considering, when the boost converter is coming, during the regenerative braking, we are naming this as load, this as the source. Now how do I control S2? Okay, how do I control S2? And same thing, whatever that we did in the converter fed DC motor, we need to decelerate under constant torque. Torque developed by the motor should remain constant. It can remain constant only when phi and Ia are held constant. Okay. Now What I'll do is, if I keep Ia constant, my torque will remain constant. The developed torque by the motor remains constant. So what I'll do is, I'll take a reference current, a constant value of Ia, okay, a constant value of Ia, okay, this is the I reference. I'll close the switch, Ia increases. I'll open the switch, Ia decreases. So I'll control the current within a hysteresis band and small band, okay, close, Ia increases, open, Ia decreases, okay. So Ia is approximately constant, therefore torque developed by the motor remains constant. So I have a deceleration, and the deceleration rate remains constant. So in this circuit, if you see, the stored energy in the armature is being fed back, there is no mechanical input, so therefore speed will fall. So if the speed falls, Eb also will fall, okay, no mechanical input, the stored energy is being fed back to the source, so omega will fall. If omega falls, Eb will fall. So if Eb falls, see in this circuit what happens. It is Eb which is forcing the current through the inductor. If Eb falls, Eb is the one which is forcing the current through the inductor. If Eb falls, the rate of rise of current itself falls, okay. It is Eb divided by L is the rate of increase in current. If Eb falls, di by dt when the current is increasing is decreases. So rate comes down, rate of increase comes down, okay. But then what happens? Rate of decay, Eb is decreasing, assuming VDC is constant, the difference between these two voltages appears across L, okay. This is falling, this is held constant, therefore voltage across the inductor is increasing. As the speed falls, Eb falls, therefore the difference between Eb and VDC increases. So when the switch is opened, voltage across the inductor increases as the speed falls, therefore the decay rate is faster now, okay. Here rate of rise is slow because Eb is falling. Since Eb is falling, voltage across the inductor when the switch is opened is high, therefore rate of decay increases, okay. So if you see in the oscilloscope, so you will get some sort of a waveform like this. Current is slowly increasing and falls faster. Current is slowly increasing, falls faster, okay. Slowly increasing, falls faster. So as speed falls, current increases slowly, decreases faster, okay. And after some time, Eb has fallen to a so low value, you may not be able to control the current, okay. So braking under constant torque is possible till a certain speed. Beyond that, it may not be possible, okay. So see that there is a change in the switching frequency also. Current increases slowly, decreases faster, because here Eb is falling, forcing function has fallen. Now here the voltage across the inductor, VDC minus E0 or EDC minus EB, EB is falling, VDC is held constant. So voltage across inductor increases as omega decreases, decay is faster, yeah, that's about it. Rest we'll see in the next class. Thank you.